Okay, now if you open up a binary, this is the very first thing we have at the beginning of the text of the binary. We're just looking at the raw file here. We have an ident telling us an ELF, 7F ELF, which is an integer size, which is convenient. We have 111, which usually is in the ident, but it's actually the processor specification and the ND in this specification, but that's usually 111. We have different things, file version. We have an entry point where we're going to actually begin. We have the program header table offset and a segment table offset. You can think of this is part of the program headers. This is part of the segment headers. We actually have two tables used to represent how programs are loaded up into memory. One of them, the program headers, contains information like where in memory will this be, and then the sections is certain sections of the program section. So we don't have where in memory this will be. That's calculated from the program section. So do we really need these sections? And it turns out we don't. That's a lot of space that we can save if we just forget the fact that we forget needing those sections. So program header offset, we're probably going to have that always be there. Section header offset, we can put that to 0. We're not going to have a section header offset. The processor specific flags is usually ignored, so maybe we can put some code there. So it's only a long, but then we have the header size, program header entry size, number of entries. We only are going to have one. We're going to make a program with one segment, just a code segment, and we're going to make that readable, writable, and executable. We're not going to deal with other sections because that's the minimal amount of data that we need. So we can forget the rest. These will be used for section strings. That's used for the relocation names as well as the section names. So how are we going to do this? Well, we first of all need to get complete control of our environment. So what we could do is write a program like this. Text segment, that's the code segment. It's also known as text. At 0, have an ASCII string. I like gummy bears. I very much like gummy bears. So how can we output that to a file just as that? Well, it turns out the linker follows a linker script. This is a language that is sort of built into the linker, the new linker, and it tells the linker how to put together different sections. And this is what a typical, the default linker script looks like. No wonder our programs are so big. So what we can do is we can replace that with our own linker script. That's much, much simpler. We're outputting in the binary. It's going to be a 386. Our entry point just going to be the beginning. We put a symbol there, ELF at the beginning. And then we're going to output the text segment. And that's it. We're going to output that beginning of 0. So how you want to compile this is you can compile it with the T argument, specify your linker script, and then have another argument, no standard library. We're not going to link to anything. No standard lib. We're not going to link to anything. So that's smaller. That's 28 bytes. That's probably our string. So we just successfully compiled an assembler program to a string that says that you like gummy bears. So now we can do whatever we want. We can manually write an ELF header and output that. So this is what our ELF header looks like. We have our beginning, 16 bytes in total. That pretty much will remain the same. It's going to be an executable, same machine, version 1. Our entry point is start prog. We have start prog way at the bottom there. Number of program entries, we only have 1. And then we have the format of the program entry. This is loadable, offset 0 in the file. This is our virtual memory address. You can have that anywhere. This is the default for OpenBSD. You can have it almost anywhere. I think the boundary is 2 gigabytes or something. You can pretty much have the program anywhere in memory. As long as it doesn't cover the kernel. But then we have the size. And you can forget this for now, 64K. That's now in preparation of my end. But the size that we're going to load is file n. We have file n symbol at the bottom. And we're going to subtract that from elf head, which is 0. But it might not be 0. You kind of have to watch out. I mean, you can put org 0 there, but it's still going to be loaded into memory at your entry point. So you keep things, you want to keep things relative, because that may be different, unless you put org 0, but that may screw up how your binary is drawn. It's going to be readable, writable, and executable, so we can put all of the code there, and it's going to be page aligned. We align by pages, 4K pages. Now this is our program. We have no library that we can't call standard loops, we can't call anything. So we have to do direct system calls. This is system call number 1, which is exit, pretty much. And we call system calls with an interrupt. That way the processor goes into supervisor mode and goes into the kernel space whenever we call the system call. Aside from the interrupt, it's pretty much like calling any C procedure. You push things on stack and you call it. So that's a program, and we can compile it, and we can run it, and it doesn't crash. It's valid. It just exits. So that's good. We have a very small program now. That's 92 bytes worth of exiting program. But it's funny because there's actually 2 Unix programs called true and false. And they do the same thing. And they are probably bigger. Ah, they're pretty clever. I think they got it a bit smaller. 79. Well, I think it's a bit smaller. I'm not exactly sure what they did. This is the first time I actually looked at the size of their program, but this is ignored by most offloaders. So you can stick code in there. You don't have to load up code from the end of your alt header, or you can load it from anywhere. So it's a very useful format. If this is, well, that's the only one I know right now that for sure that's ignored. There are other things that are ignored too. So there's some room there. So let's make a program that has C in it instead of just assembler. We have our alt header again. We have written an assembler function. It's called sys, which is just a replacement of syscall. You have the first argument being system call. This pops that off the stack. Keeps everything else in stack. Calls the interrupt and returns whatever code you're going to have. Could be another pop at the end, but whatever. So that's our function. We look at main. Now we're doing this. We have system call number 4, which is write. System call number 1, which is exit. System call number 4, write hello world, and that happens to be 16 bytes long, and then exit. Hello world. So that's cool. The only difference here in the alt header is